Good morning, gentlemen, and happy Thursday. 1.2 is the next section that we're going over, and it's pretty straightforward. So what we talked about the other day on 1.1 was mainly population density, which is number of people per unit of area. So number of people per square mile was the most common. We're continuing on with density in 1.2, but instead of population density, it is just density. So it's mass over volume. And this is something you've seen in science before, and maybe, probably in math as well. So really, the major equation that you need to know for 1.2 is density equals mass over volume. Okay? Now, there are a number of examples in 1.2, and I encourage you to look through them. The initial exercise on the first page is pretty straightforward. It has different substances, cork, and actually, I will scroll back so you can see. It has a brick, a log, a cork, and a golf ball. And the idea here is that you need to figure out what the density of each is. They give you the weight of each one in kilograms or grams, and then they give you the dimensions. And so you have to figure out volume. So the one thing that maybe is a little bit tricky, or that you may have forgotten and need to remind yourself of, is what the equations are for volumes of different solids. Okay, so we're going to start off taking a look at example 3, because I think this is really the most interesting one, and it combines everything that you need to know for this section. So example 3 is a giant cone of road salt. So it says, before a winter storm, a pile of road salt has the dimensions shown. After the storm, the linear dimensions, so not the square feet or the cubic feet, but the actual feet, the linear feet, are 1/2 of the original dimensions. How does this change affect the volume of the pile? That's our first question. So as you may have guessed, if we take 1/2 of the original dimensions in linear dimensions, we are not taking 1/2 of the volume of the cone. We are taking way, way more than 1/2 the volume of the cone. Our first question, which is letter A for example 3, asks, how does this change affect the volume of the cone? So we're not dealing with density quite yet. We'll deal with that in part B. But in part A, we're asked to see how this change affects the volume of the pile when we take 1/2 of the original linear dimensions. Well, the first thing that we have to do is remind ourselves what the volume equation is for a cone. And it's 1/3 pi r squared times the height. And the r value is the radius of the base of the cone. The h value is the height of the cone. And so that's what this work is right here. And so if you figure out what the volume is of this cone originally, with the original measurements of 53 feet as one side of the cone, 45 feet being 1/2 the diameter, so of course the radius, then we can figure out what that height is. So using the dimensions given, the 53, and the fact that 1/2 of 90 is 45, right, that gives us the radius, we have a right triangle. So the Pythagorean theorem gives us 28 for the height. Okay, so that's of the original cone, the original pile of salt before the storm. Okay. And so if we use those measurements, we're looking at the left side of this table right here, we come up with 18,900 times pi cubic feet. So 18,900 pi cubic feet of salt. Okay. Now, all we have to do for after the winter storm, the right side of this table, is to take half of the linear measurements that we started off with here, and the only ones that we need to worry about for our equation for volume are the radius and the height. So half of 45 is 22.5, half of 28 is 14. We plug those numbers into our volume equation, and we get 2,362.5 pi cubic feet. Okay? And so if we figure that out in terms of a fraction, it becomes 1/8. You could also divide this out and convert it from a decimal back to a fraction, or simply leave it as a decimal. But it ends up being 1/8 the original volume, meaning, if we go back to our original problem, that if you take half of the linear dimensions of this particular cone, the volume decreases by 7/8. We're only left with 1/8 of the volume that we started with. Right? So that's pretty amazing that we take half of the linear dimensions, but we're taking 7/8 of the actual volume of the cone. Okay, so that's part A. Part B is talking about density. So it says a lane mile is an area of pavement that's 1 mile long and 1 lane wide, and during a storm, 400 pounds of salt are used for every lane mile. Estimate the number of lane miles that were covered with road salt during the storm, knowing that a cubic foot of road salt weighs 80 pounds. Right? That's a key piece of information. So here's the work for B. So for B, we take the original volume that we calculated from A, which is 18,900 pi. We subtract the new volume, right? This is the volume after the storm, and we get how much of the salt was actually used for the storm, which was 16,537.5 pi cubic feet. And it's perfectly fine if you don't write it in terms of pi, and you multiply each of these numbers, 18,900, 2362.5, and 16,537.5, by pi. It's fine if you multiply those by pi. The book is simply leaving it in terms of pi, so these numbers are a bit smaller, just a little bit easier to work with. And so that's how much cubic feet of road salt was used, 16,500 approximately pi cubic feet. Okay. Now, knowing that, we can use a unit multiplier here to figure out how much road salt that is in pounds. We know that 1 cubic foot is 80 pounds, and so that 16,500 pi number times 80 gives us 1.323 million pi pounds. Right, so that's over 3 million pounds. That's a lot of salt. Okay, and then the question is, how many lanes does that cover? Well, we take the number of pounds and we divide it by 400, because we know that there are 400 pounds in a lane mile. And so that 7/8 of a pile of salt, okay, that's what we used when we halved the dimensions, the linear dimensions, is 10,390.82 lane miles. So almost 10,400 lane miles of road were able to be covered in salt. Okay, so that's kind of a fun problem, I think. It's an application problem, and hopefully we're not going to need to use that much salt through the end of the year. But this is something that certainly applies to us in the snow belt, is having to figure out, all the civil engineers having to figure out exactly how much road salt is going to be used on our roads. So if you can work your way through example 3 and you understand how to use the Pythagorean theorem to find the height, and then use the height to find the volume, and then using the weight of salt and the number of pounds of salt per mile of road in order to solve for how many lane miles were actually covered during the storm, if you can do all of that, you are in great shape for 1.2. Thanks very much. Good luck on the homework, and let me know if you have any questions.